look into some operation on these files and directory to understand the functionality of the file system. Begin with the very first operation to a file, that is opening a file. And this is provided through open, system called open. By open, we can create a new file. Always those creation belongs to, happens at a certain directory. So as an effect of the opening a file with a new name, then what it does is that it first allocate a space, allocate an inode, and given the inode number for that, and then what? Register this inode to a specific name in a directory. So by updating the directory's list of the files, and give it to the application program to use it. That is basic operation, basic behavior of this open system call. And if open system call receive a name that is already exists, what it does is make it available, make process, the caller process to access this file. And another interesting thing is that you can open up the file with the truncate mode. O trunk 이렇게 하면 되죠. 그럼 어떻게 돼요? 일단 여러분 truncate 나오는 순간 항상 조심해야 됩니다. trunk 하면 어떻게 돼요? Just goes away. I mean, so if you open up the file with the truncate mode, then the size becomes 0 and all contents are just cleared up. That is another possible use case of open system call. And open system call returns so-called file descriptor. File descriptor is what? Is a non-negative integer that is belongs to a specific process. It starts from 0, 1, 2, 3, and so forth. And the maximum number of the file descriptor a process can have is limited by the operating system, because that the maximum number represents the number of the files that the process can open at the same time. And we don't want a single process to dominate a lot of the files and consuming a lot of time for opening them and using them at the same time. So usually it is limited anyway. And it becomes like a pointer of the file object. And here the question is that, okay, I know that there is a identifier of the file, and you mentioned that as inode number. Then why don't we just point specific file by inode number? Why do we need a file descriptor?
Each process may have the same inode.
Yeah, but it is all right that two processes can open the same file at the same time. Then why does just indicate a file with this inode number? Inode number can work as a universal identifier to a file.
It takes a long time to search.
That is not, yeah. File descriptor also, we will see that, but file descriptor also will be related to inode number. So the efficiency is not a big deal here. That is because inode number itself is insufficient in this purpose. For why? Because when we open up the file, then if the process will have a context in using that file. So inode number will represent static location of the file that is concerned, but process needs to contain some context in using it. Why? Because in default, when we use a file, sequential read and sequential writing happens. We don't say that update this location of the file by this data. We don't use a file in that way. Later, what we did is that read next 30 bytes. Then what it means by next? Next from where? The last point that I have access so far, which means that when we use a file, a process, when a process use a file, it maintains context in using the file. See the point? That is a very big difference from using array. And here, when we use a file, we use file as a string. 이해돼요? offset 필요하다. 교과서를 미리 읽어온 사람의 질문이죠. 네. There should be a cursor to indicate to which point, up to which point the file has been written or file has been written, has been read or has been written. 그렇죠. 우리 되게 아무 의식 없었는데. Think about a read operation. When we say read, do we say the position? We mentioned the file ID. We give a file ID or file descriptor, and then what? We give buffer name, and we give how much byte I want to receive from the file. We don't say that from which offset data should be read. We don't say it in that way. Then from which location? That cursor is maintained underneath the kernel. So I know this cell, I know number itself cannot really represent that contextual information. So file descriptors are needed. See the point? So file descriptor not only indicate a target file, but also it indicates the context of the process in using that file. See the point? Okay. So I don't really need to explain it about the read and write operation because this is basically what you already learned from C programming course. Good job. So, but I will just give you explanation for this example taken from your textbook. So cat food. Cat is to print out things on the screen. Roughly speaking. 네, 사실은 아니니까 마음에 많은 부담이 있지만 오늘 지금 놀러 가야 되니까 더 이야기는 못한다. 마음을 가지고 제가 이야기했습니다. So when I say cat food and contents of the food will be printed on the screen, roughly speaking. So here you see that the food has a hello, so hello will be printed out. But in this example, these commands are actually executed through a system tool called strace. Strace is a kind of a system tool, or I say debugging tool, that printed out all the execution of invocation of the system call along the program execution. So this is widely used for looking into what kind of things happen and to debug the program or analyze the program execution. So you can see that the execution become really verbose. I mean, operating system become really verbose when strace is used to display all the receive and return needed information through system call. 이거든요. 이해돼요? So this will record all steps of the system call involved in the program execution. What you see here is that cat program first open up the foo by calling open. Here the name is given foo, and these are the options given to this system call, and it returns 3. Why it is a 3? Because by default, process have a 3 file descriptor. 0, 1, 2, what are they? Standard input, output, and standard error. So they are just open up default. So if we open another file, then 3 will be received. Okay, and it reads the 3, and this is the contents of the buffer as a result. And here saying that I want to receive up to 4 kilobytes to a certain buffer, and what the system call deliver is these content and say that I just gave you a 6 byte. Check this byte, 6 byte from the buffer. So this one printed out those 6 byte to file descriptor 1, which is standard output, right? And here you say that, okay, the printing was successful for 6 bytes. And then what? Hello appears, and then what? Read another byte, another 4 kilobyte, another byte up to 4 kilobyte from file 3. But it returns 0, saying that the file is just ended. Then it finds that, okay, this was done. So it closes up the file and terminate the program. This is basically how open and read and write are used in this example scenario. Question? I think I explained the same thing as I teach open source software project course. So it's become really primitive things.
Well, you said before that the cat prints out the content of something in roughly speaking. So is there a reason why you said roughly speaking? there
Because
might be
CAT is
some-
not originally for that purpose. CAT is a much bigger tool than just printing things out to the screen. Okay, so basically file is to be read and written sequentially through by using the read and write operation, but we can read data on an arbitrary point by first relocating the cursor. And the operation for that relocation is called it as a seek, and the library name is lseek. And what it does is that it receives the target offset and update the cursor or current offset to the specified one. So seeking, what is a seek in a hard disk driver? It is moving on. That basically what seek means is what? Thinking about a magnetic tape, and what you're doing is what? Pressing forward and backward to find the exact starting point of a certain song. That is a seeking. That is exactly this means. Why? Because originally, long time back, even today, long time back, the storage magnetic tape was largely used for storing. You use that as a storage device media, magnetic tape. Even today, magnetic tapes are widely used for backup. 사실 잘 보면 뭐예요? Once you carefully understand hard disk drive, this is nothing more than what? Spider magnetic tape. Magnetic tape 여러 개를 spiral이거든. It is like a multiple magnetic tapes are structured as an onion. That is a hard disk drive. And even today, magnetic tape is good backup media devices. Why? Because they can store the data safely for a long time. So once a file is open, the OS track the current offset. You can think of it as a kind of a cursor. It exists underneath the kernel layer. So to indicate the position for the read and write, and we can explicitly move that point to a random place. Of course, it takes some time. It is far more efficient when we read and write a file sequentially. And if we randomly move these pointers, then obviously those accesses will be more costly than ordinary sequential read and write accesses, but this is possible. Okay, and this figure describes the data structure inside of the kernel for holding these information for the file descriptor. So this is the application program side, and this is the kernel side. And for the application program, file descriptor is actually, it's just a number. I mean, it has no mean of a link. It's just a number. Yeah, 이거 사실은 없어요. There is no link. This is just number. And when you call on a system call, it just to keep this number to indicate the file that you had opened before and has been used so far. 링크 없습니다. 그냥 숫자밖에 없어요. 숫자밖에 없어요. 아까 여기서 봤죠? 숫자밖에 없어요. 숫자로 이야기하는 거예요. 네. 저 커런트 오프셋이 유저 레벨에 남아 있어요? 없어요? 없어요. 그냥 여러분은 숫자로만 이야기하는 거예요. 커널한테 시스템 콜 날릴 때 숫자만 날라와요. And but those cursor and all info, or I say current offset, and I know that actually points to the file object. All those information are maintained in so-called as a file table inside of a kernel. And this is the actual place where all those information are managed. And those management is by operating system. And suppose that two processes exist and they are independent processes and they are opening the same file at the same time. Then two different entries in file table, two different entries will be created in a file table. Why? Because those two applications may have a different context, of course. And these entries will not be shared across a process, but there is some exception. What's that exception? If it is a parent's file descriptor and one child process is created through fork, then the child process will inherit exactly the same meaning, same file descriptor of its parent, so that when it mentions the file descriptor, the kernel will understand it as the same meaning as its parents, so that they can share one file genuinely. So we propose that a parent process open up the file and has been read so far. So for like it open up the file and read for like a 10 offset, and then it create a child process, and then the child process read the next 10 offset from the same file, and then parent process as a parent process, it try to read on the file. Then what the parent process read is not 11th offset and so forth, but it is the 21st offset and so forth, because this page table entry was updated by the action of the child process. This is very intentional. This is a very intentional. Why? Because child process is created to share the resource of the parent process. And within the same process, we can allow a process to create a new file descriptor and get a new number, but from existing file descriptor, not a new one, but existing file descriptor. It's a kind of duplicating the same page table entry and having multiple alias on them. And by how? By duplicate system call. Or I think you have already have used the dup2, a variant of this duplicate system call for replacing existing file descriptor with a different contents. So that is how this system call manipulate the file table inside of a kernel.